All right, let's have a look at this homework here that's due on Friday. So what we got 2 problems for principal stresses, and then we've got 2 problems for Morse circle. And I could probably do one of each if you'd like. So for the principal stresses, are there questions on that specifically, or do you want to look at one of those? Like one, actually it's 201, I'm sorry, so let's roll up there. So we could look at 202. That might be a good one to go through. Okay, so let's have a look here. So 202. All right, now you already did 191 and 192, and this is very similar. It's got one important difference though. So what you do, you look at what you're given, and you're given a plate or something like that that has X and Y stresses on it. So the first thing you want to do is you want to write them down, okay? So you want to figure out what the X and Y stresses are, okay? And you just look at the sketch and you write them down. So there they are. So sigma X is positive 60, it's pulling. Sigma Y is positive 20 because it's pulling also. And then the shear stress is 15. Now the shear stress on the reference plane goes up. If you were to, that were a board and you nailed it into the wall and pushed up on the right hand side, the board would go counterclockwise, and that means it's positive, okay? So counterclockwise means positive, so that's a positive 15. Now on the previous problems you did, you were just given stresses in the X and Y directions and then told find the stress on such and such a plane. The difference with this type of problem is now you're not told to find the stress on a given plane. You've got to find the maximum and minimum stresses. So what you need to do is first to find the plane on which they act, okay? And that uses this tangent 2 theta formula, which is on the front of your formula sheet. So and that's equation 27. So you want to go ahead and plug into that, okay? So it's tau xy divided by sigma x minus sigma y over 2, and that's equal to the tangent of 2 theta. And when we plug all that stuff in, we get 0.75. So when you do an arctan of that, you get 36.87 degrees. Now that's the 2 theta 1 angle. When you take half of that, you get the actual angle, which is 18.43. So what this is saying is one of the principal stresses, either the max or minimum stress, acts at 18.43 degrees from the vertical reference plane. That's what that means. Okay. Now the other principal stress acts 90 degrees off of that, so if you have 90, you get 108.43. So the angles at which these principal stresses act are 18.43 and 108.43. Now the formula though uses the 2 theta angles, so you double the stresses to get the doubled angles. That's what goes into the formula. Okay, so the one difference on this, and it's important that you get this, is you have to find the angle first. Okay, so we went ahead and did that. So the angles are 18.43 and 108.43. So the doubled angles, which go into the formulas, are 36.87 and 216.86. Okay. So once you've got those, you take those angles and you plug them into equation 25 to find the normal stresses. Okay. So these are called the principal stresses. So all we're doing there is taking the angles that we just found and plugging them into the general equation number 25. It's just like the stuff you did before, except you have to find the angles first when you're doing this, okay? So you run that formula, plug in the 18.43 times 2, which is 36.87 degree angle. Run the numbers, and what you'll find is the stress at 18.43 degrees is 65 megapascals. okay? And that's called sigma 1. All right, and now you can do the exact same thing for the other angle. 108.43, 2 times that is 216.86. So you can just do it again for the other angle and find the stress on the plane that makes 108.43 degrees with the vertical reference plane. Okay. And what you'll get there is 15 megapascals. So those are the maximum and minimum stresses acting in the element. So when I look at those, I can see if I'm going to design this thing, I'm going to design it for 65 megapascals tension. That's what I want to do, all right? So we're doing all right with that? Now, there's a shortcut formula, too, that you could use if you want, okay? And you can use sigma x plus sigma y as sigma 1 plus sigma 2, because we found sigma 1 already at 65. So if you take sigma x, 60, plus 20 more for sigma y, and take away sigma 1, 65, you get sigma 2. It's just a quicker way to get sigma 2. For me, if I'm using a spreadsheet or something, I'll just go ahead and use the formula to get that second answer. If I don't have a spreadsheet, I'll use that shortcut formula. It's quicker. Okay, either way, it's the same answer. All right. So we good with that? So if you're told to find the stress at a given angle, you just plug the angle in and find it. If you're told to find the maximum stresses, you find the angle first using the tangent to theta formula, then plug that in. That's the difference. Okay. Now we also want to find the maximum shear. Now the maximum shear acts on a plane that's 45 degrees from the maximum normal stress, the principal stress as it's called. So the principal stress acted at 18.43 degrees. Add 45 to it, you get 63.43. Double that, you get 126.86. So that's the angle at which the maximum in-plane shear stress acts. So I can just take that angle and plug it into the general shear equation right there, which is equation 26. Run the numbers, and what I come up with is the maximum shear in plane is negative 25. Okay. So what I've got now for in the plane is the maximum shear, it's negative 25. I've also got the maximum normal stress in the element at 65, and then the other is 15. Right? So those are the numbers that I start to look at to figure out how to design this thing, because they're the biggest. Okay. Now on the plane where I've got the biggest shear stress in plane, I've also got the average normal stress. That acts on the maximum shear plane. So that's just the x and the y, 60 and 20, add them up and divide by 2, and you get 40. So that's the normal stress on the plane that has the maximum in-plane shear stress. Okay. So we good with that? Do we got any questions on what we're talking about here or how we go about finding it? Or are we okay with that? Okay. Now there's one other thing you have to check, and that's the shortcut formula for tau max. Okay. Now we already know that tau max in plane is plus or minus 25. Okay, because shears always come with a plus or minus. Okay, but we want to be sure we've got the absolute maximum shear in the element, and the way to check that is to use this shortcut, another shortcut formula, that tau max is plus or minus sigma max minus sigma min over 2. Okay, so if you take the maximum shear normal stress in the element, take away the minimum shear stress in the element, and divide by 2, you'll get tau max. Okay. So when I do that in plane, if I take my maximum in plane normal stress, that's 65. I found that up above. And if I subtract off the minimum in plane normal stress, which is 15, and I divide by 2, I get 25. And it's a plus or minus value. And sure enough, that's what I got when I did the little process up above, where I found the angle and plugged it in. Okay. But there's another possibility that I have to check, because sometimes I have to check and see if sigma z is the minimum. So sigma z, when you're doing biaxial loading, is always 0. Okay, always. Okay, because you just got loads from 2 directions, so there's no z stress. So what I want to do is plug in 0 for sigma min. My tau max is still 65. I get plus or minus 65 minus 0 over 2. And that's plus or minus 32.5. That's an out-of-plane tau max is what it is. And so if I'm going to design this plate, that's the shear I want to govern for right there. It's the absolute biggest one. So the out-of-plane shear stress may or may not be the maximum. It just depends on how the numbers work out. But you do want to check it. Okay. So we got any questions on that? So what we got there is we got sigma 1 at 65 at an angle of 18.4. Sigma 2 is 15 at an angle of 108.4. Now, what you call sigma 1 and what you call sigma 2 are not really set in stone. You could switch those answers if you wanted to. The important thing is that the 65 acts at 18.4 and the 15 acts at 108.4. What I called sigma 1, you might call sigma 2. It doesn't matter as long as you've got the right stress at the right angle. You can really, call it whatever you want. It doesn't matter. Okay. So the important information is you've got those max and min stresses at those particular angles. And also, if you're going to design this thing, you want to design it for a normal stress of 65. Okay. Tau max in plane is negative 25 at 63.4 degrees. Now the deal with that is tau max. There's kind of two ways to look at that, I guess you might say. You could say it's negative 25 megapascals at 63.4 degrees. Now I guess you could also say that tau max is positive 25 megapascals at, you got to add 90 to this, that would be at 153.4 degrees. 90 degrees off the positive 25 is a negative 25, okay? Or excuse me, other way around. 90 degrees off the negative 25 is a positive 25. They're just 90 degrees apart, okay? You could also say that tau max in plane, you might also say it's plus or minus 25 too. Okay. Yeah. It's 25 however you cut it, whichever direction it's acting. Okay. Now the average normal stress is 40. That acts on that tau max plane. And then tau max absolute is the one that's out of plane. It's plus or minus 32.5. So, we okay with those answers, Sarah? Any questions on that? All right, now I'd like to be able to draw sketches of this stuff, if there aren't any questions there. And I like to be able to do that because I want to visualize what's happening here, okay? So, that's why I like this method of approaching the calculations. What I like to do is I like to find the angles at which the principal stresses act, plug them into a formula. When I do that, I know that if I plug 18.43 degrees and double it for the 36.87. And if I plug that into the formula, what comes out is 65. Okay? I know that's one of the principal stresses, and I also know that the 65 acts at 18.43. Okay? Then when I plug in 90 degrees more than 18.43, I get 108.43. Double that, I get 216.86. When I plug that in, I get 15. So what this does is it tells me not only what the principal stresses are, but also what angle they act at. Okay, that way I can draw a sketch real easily. So when I draw that sketch there, I know at 18.4 on that plane that I'll mark here, these planes here, the normal stress is 65. And I also know 90 degrees off of that on these planes, I've got 15. Okay? By using that approach on the equations, I can draw a sketch up and visualize what's happening a lot easier than other methods I might use. The other method I might use is that radical formula, which is 28. It's sigma 1 and 2 is sigma x plus sigma y over 2 plus or minus square root sigma x minus sigma y over 2 squared plus tau xy squared. The problem with that equation is I don't know which stress goes at which angle. There's actually ways to figure it out, but it's just simpler if you want to draw a sketch to just find the angle, plug it into the general equation. That way you got a stress and an angle, you know. Okay. Okay. Same thing with the shear. When I ran the numbers, I know the in-plane maximum shear acts at 63.43. And when I run the numbers on that, the shear came out to be a negative 25. So when I do the sketch, when I draw a 63.4 degree angle for that plane there, the shear on that plane is negative. Okay, it rotates the element clockwise. The shear on the plane 90 degrees from that is positive. Okay, so by plugging the angles into the equation, I can draw the sketches more readily. Okay with that? Any questions? All right. Now the other thing here is this tau max stuff. Okay, tau max acts at 45 degrees with sigma max. But there's two ways you could look at it. One way is if it's in plane. Okay, if it's in plane, you could draw in an element that makes 45 degrees with the principal stress, normal stress element there. See how these two elements are oriented the same way? That's how you get to the in-plane stresses. Okay. But the other possibility is it's out of plane, and that's the one that governs in this case. If it's out of plane, the meaning of that is you've actually got 2D stress, but it's a 3D element. It actually looks like that. Okay. And if you're out of plane, what's happening is the maximum shear is like that. It's running 45 degrees across that edge. And that's what's happening in our case, is we've got a tau max absolute of 32.5, and it's acting on that plane that runs 45 degrees across the edge there. Okay. So again, if you're going to design this plate, you better design it for a shear of 32.5. That's what you want to design it for. So you always want to be checking that out-of-plane possibility for tau max. Take your absolute value maximum normal stress minus 0 and divide it by 2. Okay. So we all right with that? We got any questions on that bit? Okay. We're good. because we've also got the more circle stuff to do. Okay. Y'all want to just take a break here, and then we'll look at the Morse circle. That'll take a little while. Might be good to take a break before we do that. So we can take 5 minutes or so. So we'll kick up here about 10 till.